Hello, welcome to my session, Analyzing Execution Plans Like a Pro. Thank you for attending this great conference, great event, and also attending my session. I hope you enjoy the conference so far, and I hope that you get the most out of my session. My name is Glantser. I'm a data platform MVP. I am also the CEO and founder of Madeira Data Solutions. We are an Israeli-based company. I'm from Israel, but we provide solution services to customers worldwide. I have about 25 years of experience with SQL Server and with, in recent years, also with the cloud, with Azure Data Services. And I love execution plans. I love performance tuning in SQL Server. And my goal in this session is to show you lots of things that you can do with execution plans, things that you can find and understand where the bottlenecks are, where the problems are, and what you can do about them. I see a lot of common things that people do that people maybe don't understand, and I would like to share as much as I can with you in the next hour. So let's start. This is a completely hands-on demo intensive session, no slides. I have a few slides later for just for a summary to recap, but all the session will be in Management Studio. So let me switch to Management Studio. Don't worry, I will make it available for you. You will be able to download all the scripts, everything I showed you here. There's lots of stuff here to show you. You will have everything. First, we have the setup. I've already executed the setup, so this will create a database for you with some tables and some data. And then we start here. So the first thing I want to talk about is compare session settings. I usually start with set statistics IO on when I troubleshoot query performance, because I want to look at the logical reads. In most cases, if you can reduce the number of logical reads, you can also improve performance. And of course, include actual execution plan. Those are the two main tools that I use when troubleshooting query performance. Now, here is a scenario for you. Users complain there is a report that takes too long to run. The report is running some stop procedure behind the scenes. And they ask you to check what happens. Why does it take so much time to run? So what you do, you run either extend events or profiler. Let me show you extend events. So I have this monitor RPC executions. Let's set up an event session using extend events. Create event session. We know that we have an application. In my case, I called it problematic application. This is the name of the application. I put it in the connection string. So what I'm going to do, I'm going to add an event for RPC completed. RPC stands for remote procedure call. So this is whenever the application executed the stop procedure and it completes, we get this event. And I want to add this filter client application name equals problematic application, because I just want to filter this specific. I know that the problem is there. I don't want to get events from all applications. A best practice for this is to add more filters. Okay, for the sake of this demo, this will be good enough. But if you're going to run this event session in a very busy production environment, and this problematic application runs many different RPC events or different stop procedures, then this might be too much. It might be too heavy. So you need to be careful with that and to limit the events to only what you need, either by host name, login name, maybe something else, maybe the duration, whatever. Okay, so make sure that you filter it appropriately. And also, we have several targets. This is not a session about extend events, but just that you know, you have all kinds of targets. In this case, I use the ring buffer, which is memory. So write the data into memory. And I want to limit to the five recent events. This is good enough for me. So let's set up this event session. And let's start the event session. Now, I'm going to switch here. And I have this problematic application. So this is a console application, which I wrote in .NET. And it does all kinds of things behind the scenes. So this will simulate some application, whatever. It runs all kinds of stop procedures behind the scenes. And it's running right now. And as you already know, we have this event session, which gets all the events of RPC completed coming from this specific application. So now we want to see what happened. So I have this query here. It uses xQuery. You need to be familiar with xQuery if you want to write code that interacts with extend events, because everything is inside XML. The event data is XML. So we get the XML here from the DMVs that we need, and then I extract the relevant information. I want to look at the statement text of each event of RPC completed, the event date time when it happened, and the duration in microseconds. Okay, so this is the query. Again, you have all those scripts. You can use them later. And as you can see, I have the last 5 events at each point in time because I asked for maximum 5 events. And I have some instances of this specific stop procedure, get invitation by status coming from the application with a single parameter status ID, each time a different value of this parameter. We have the event date time of each one, and we have the duration. As you can see, the average duration is around 4 or 4.5 seconds. And this is too long. Okay, so users complain, they say this needs to run really fast, like less than a second. Something happened, this is not good. We need to check what happened. Okay, so now that we have this, we can take a specific execution example. Sometimes you have many parameters, and you want to. My goal is to run the stop procedure inside Manage Studio using the include actual execution plan so that I can investigate what happened. Okay, so for this, I need an execution example. Sometimes you have lots of parameters. You don't really know how to run the procedure to simulate what the application is doing. So this is why I'm setting up an event session so I can take an execution example. Now let's go back here. I've already copied and pasted this execution example here. And now I can run it and see what happens. So as you can see, it took around 2 seconds. Okay, let me run it again. Okay, even 0 seconds. So this is really fast. Everything is okay. This is great. But this is not what happens in the application. So again, this is what what the users see. Again, the 5 last executions. Sometimes it's even more than 5 seconds. And when I run the stop procedure from Manage Studio, it takes 0. Less than 0 seconds. Less than 1 second, of course. And we can look at the execution plan. So here's the execution plan. We get a clustered index scan of the invitations table. By the way, let me show you the stop procedure itself. So I'm using the DemoDB. This is part of the scripts here to set up the DemoDB. And we go to stop procedures, get invitation by status. Let me show you the code. So it's a very simple stop procedure. It accepts a single parameter status ID of data type tinyInt. It selects top 10 from the invitations table, where status ID equals the parameter, ordered by creation date time ascending. A very simple stop procedure. Again, if we go back to our plan, it does a clustered index scan of the entire table, then sort everything by date and time to get the top 10. It happens in parallel. Then we need to gather all the threads together, and because each thread retrieves top 10, we need another top operator to get the top 10 based on the order by from all the threads. Okay, this is the plan. And it runs, for me, as you can see, it runs for less than 1 second. So it's very, very good. But users continue to complain, look, it runs for 5 seconds. Something is wrong here. We can also see that we have a missing index recommendation, this one in green. We can right-click missing index details. And this is a nice feature. The optimizer, while optimizing the query and trying to generate different possible plans, it says, look, if you add this non-clustered index, give it a name, whatever, on the invitations table on the status ID column, and add these columns as included columns, this could really benefit this query and improve performance. In fact, it could improve performance by 23% on average. Okay, so this is what the query processor says. And it's nice, but there are several problems with this feature. So you need to be careful. Don't just apply these recommendations blindly. First, it's not a very smart feature. Okay, the algorithm is quite basic. It simply looks at your query. Sorry, this is the query. And says, okay, you filter by status ID, so let's create an index on status ID. And you need all of those columns. Let's put them as included columns. That's it. Okay, so it's quite simple. You can do it yourself. And the second problem with this feature is that it only looks at this specific query. And this is important. This is actually dangerous, because if you let SQL Server now create this index, it will probably, yes, it will improve performance of this specific query, but it doesn't take into account the entire workload. And it might affect in a bad way other queries. And if you just blindly accept those recommendations, you might end up with many, many indexes. and it will affect all of your DML operations, and this can be risky. So you need to take this into account and be careful with applying those recommendations, but it certainly can be a nice thing to look at and consider. Okay, so what happens? Why do we get very good performance? Why users of the application get worse performance? Some of you might already be familiar with that, but if you're not, let's look at the plan cache. Okay, so I select from procedure stats. This gives me some statistics about store procedures currently in the plan cache, and I want to look at the plan of each one, and I want to filter on this specific store procedure and this specific database. And as you can see, we have two instances of the same store procedures, two execution plans in cache for the same store procedure. Okay, so now we're starting to get an idea of what's going on. And I can tell you based on the execution count and also the duration that this execution plan belongs to the application. By now, it ran 72 times. And this execution plan belongs to us from SSMS, Maintenance Studio. I ran it 3 times already. As you can see, the average duration for Maintenance Studio is around 600 milliseconds. And the average duration for the application is more than 4 seconds. Okay, you can see the difference. This is the execution plan I just showed you. This is our execution plan from SSMS. And this is a completely different execution plan that the application is running. Okay, so this is why we have different performance because we have different execution plans. Now it's weird because our plan with a clustered, a thick arrow and the clustered index scan looks like a poor plan in terms of performance, while this plan for the application looks a lot better. We have an index seek, and the arrows look a lot thinner, so it looks much better, and somehow it's the opposite. Okay, you need to remember that when we look at the plan from the cache, as we are doing now, we only get the estimated plan because it doesn't represent an actual execution. Okay, this is the plan as it was compiled initially with estimated values. So if we look here, we only get estimated values. We don't get actual values. And this is a bit misleading, but when we look at the estimated plan, the arrows represent the number of rows that flow through them, but only the estimated number of rows, because this is only the estimated plan. We don't have any actual values here. While when we look at, where are we? When we look at our actual plan, this one, this is an actual plan. As you can see, we have estimated values and actual values. And now when we look at the arrow, it represents the actual number of rows. So this can be really misleading. You need to be careful there. And if we go back here, so yeah, this looks nice, but this is the estimated. And probably, because we know it takes a lot of time, more than 4 seconds, probably the problem here is the gap between the estimated number of rows and the actual number of rows. And we will look at this later. Okay? So we know we have 2 different execution plans. We need to understand why. Why do we have 2 plans? Why am I not reusing the plan that the application is already using and I get a different plan? So we need to do something else. We need to look at plan attributes. Each plan in cache has several attributes associated with it. And one of the attributes is set options. Each plan has set options. If we look at the plan, here is my plan, actual plan. Right-click properties on the select operator. We have the set options here. So each plan has several set options, associated with it, like ANSI nulls, ANSI padding, and so on. Each one affects the behavior of the session in some way. Okay, so for example, ANSI nulls mean what happens when you compare something with null. So if it's true, the definition of ANSI nulls, it's that it always returns false, a false result. If it's false, it means if something is null and you write where a column equals null, it will return true if it's actually null, and you don't have to write is null or is not null. Okay, so it affects the behavior, and because it might affect the results of your queries, it also might affect the plan, the best possible plan for your query. So whenever something changes in those set options, for the same query, you will get a different plan. If you have 2 different sessions with 2 different set options, some combination of the set options, they will get different plans. And I want to show you, we look at the plan cache again. I want to show you what are the set options for each one of those plans. So as you can see, they are different. The set options is a bitwise representation, so each bit represents a different set option, and we get an integer that is the summary of all the set options together. We still don't know what is the difference, but we can see that there is a difference. And the fact that there is a difference This is the reason why we get two different plans, because for each different number, we will get a different plan. Okay? Now we want to see what the difference is. So I have here a series of IIF, or you can write it as a case expression if you like. And I want to use bitwise operator to get a specific bit and a specific value of each one of the set options to compare between them. So here it is. As you can see, ANSI null is true for both sessions, ANSI pending is true for both sessions, and so on. If you look at it, you can see that everything is the same except for Arita board. So for Management Studio, Arita board is true. For the .NET application, Arita board is false. First of all, let's talk about what Arita board is. How does it affect query plans or queries in general? So Arita board means two things. If you have a divide by zero error in your query, or if you have an overflow. Okay, you try to convert something from int to tiny int, for example, and it's more than 255 or something like that. Okay, so divide by zero and overflow. If Arita board is true, this will stop execution of your query. This will provide an error. If Arita board is false, you will get null value when you try to divide by zero, for example. It will not provide an error and stop execution. Okay, so it affects the behavior. Now, why do we have different values? Because when .NET application starts, opens a connection, it initializes Arita board to false by default. This is part of the driver, the .NET, the SQL Client driver. It will set Arita board to false, and SSMS, which uses the same driver behind the scenes. It opens a connection, set Arita board to false, but then it overrides it and set it to true. I want to show you this. I have here another event session, monitor logins. The event will be login, so every time we have a new login, a new connection for SQL Server, we get this event. I want to collect option text. Okay, I will show you what it does. And I want to get the client application name. I want to compare between a new session from the .NET application and a new session from SSMS. Let me close the application, and then I will open it again later. And now I want to filter only on either connections coming from our applications or coming from Management Studio. This is the name of the application when you open a new query in Management Studio. Okay. I want to get the login. I also want to get the SQL batch completed event for each one of them, because I want to show you what happens when you open a connection with the same filters. Again, go for the ring buffer and start the event session. So first, let's open, where am I? Let's open the application again. Okay, so now the application opens a connection and starts running all kinds of things within this connection. So I want to get the event of the login and also some batch completed events. And again, I have here a query with xQuery to get relevant information from our event session. Now you can see this. This is what I did behind the scene to simulate the problem. Okay, so you shouldn't have seen that. You should ignore that. Anyway, we get the login. Okay, so we get the login event, and because I asked for here set collect option text equal 1, I got this event text, and I've already pasted it here. So this is a set of commands that each time you open a connection through the SQL client, whether it's from SSMS or .NET or whatever, it will run for it to initialize the session. And as you can see, one of them is set Arita board to off. So by default, it sets everything to off, every connection, Arita board to off. And if we do the same thing with Management Studio, so I click new query, this opens a new connection, again, a new login event, and I go here and run this again. So this is the previous login from the application. Here is a login coming from Management Studio, as you can see here. We get the same set of code because SSMS uses the same driver behind the scenes. But then, look here, SQL Server Management Studio also runs a few statements, a few batches after the login. One of them is this. And again, I copied it here. So it runs this. And this also initializes some things. One of them is Arita board. So it overrides the previous set Arita board to off, and it sets Arita board to on. I can also show you, if you look in Management Studio, query options, advanced, you can see set array abort is set to on by default. You can change it for your query, or you can change it entirely in the options for all queries, but this is the default. Microsoft recommends to set array abort to on, but Microsoft itself also develops the SQL client, which sets array abort to off, and it stays like this for backward compatibility. And now we have a conflict. Every time you write a .NET application, unless you do something else, by default it sets all connections array abort to off, which is not a recommendation, by the way, by Microsoft. I will show you that in a minute. And every time you open a session, a query in Manage Studio, you set by default array abort to true. This means that every time you want to troubleshoot something, like I did now, okay, something that the application is doing, you want to look at the execution plan, you are actually looking at a different execution plan. You never look at the same execution plan as the application. They might get the same plan, but those are two instances of the same plan in the plan cache. And sometimes, like in our case, we get completely different plans, okay? Let me show you, not here. Okay, we can drop this one. Thank you. Let's close it. And we can close this one. And let's take this one. So this is the documentation by Microsoft about set array abort. And it says here, we have a warning. The default array abort setting for Management Studio is on. Client application setting array abort to off, which is a default. It's not something that you do. This is always off. Might receive different query plans, making it difficult to troubleshoot poorly performing queries. That is, the same query might execute fast in Management Studio, but slow in the application, just like I showed you. When troubleshooting queries with Management Studio, always match the client array abort setting. So we have a warning, but nobody reads it. Most people are not aware of it, and we have a problem. Okay, so you should be aware of it, and you should understand what to do. So the best practice is to set array abort to on. So what you should do in your applications, you should have a data access layer before going to the database, and whenever you open a new connection, you should set array abort to on. This is the best practice. Almost nobody does that. So at least when you troubleshoot plans from Management Studio, you should match the array abort setting of the application. You should set array abort to off. And now, if I run the same store procedure with the same parameter, everything the same, suddenly it takes time because now I'm reusing the same plan as the application. Now I'm just like the application with the same set options. Okay? Now it's really taking a long time. 11 seconds. Okay? So this is, as you can see, the same plan as we saw in the plan cache. Suddenly, the arrows look a lot thicker because now they represent the actual values. And as you can see here, the estimated number of rows is only 10. This is what we saw in the plan cache earlier. But now we can see that the actual number of rows is 1.5 million. This is a huge gap, and this is the problem. Okay, so we found the problem. The optimizer estimated only 10 rows coming from the invitations table. Based on 10 rows, it says, okay, let's use a nested loops inner join, which means I'm going to do only 10 key lookups. Okay, so index seek with key lookup, only 10 key lookups, a great plan. But in reality, SQL Server has to perform 1.5 million key lookups, which means we get this number of logical reads, which is a huge number of logical reads compared to only 10 rows that we need to return back to the client. Okay, so this is the performance problem. And the plan that I was getting in Management Studio didn't have this problem. So the optimizer realized that we actually need a lot of rows. Let's just do a scan once instead of 1.5 million key lookups. So this is how to troubleshoot. Now, how can we solve the problem? So currently the users are still complaining. What can we do? There are several things we can do. One of them, to begin with, assuming this is a temporary situation. So usually everything is okay. For some reason, there was a recompile, and now the store procedure from the application is getting the worst plan. What we can try to do is to run sp recompile for the store procedure and telling SQL Server, okay, try to recompile it again. Maybe in the next execution, it will be okay. And now, if we look at the plan cache again, we can see that I have only my execution from Management Studio, the previous one. Okay. If I set array abort to on again, and run it again, okay, so now we get the good plan again with the clustered index scan. If we look now, then as you can see, the application, okay, so we did recompile. So the next time I ran it, now I get a new plan, the good plan from Management Studio, and it's 1. But also the application started to run the procedure after there was a SPV compile. It also got a new plan, but this time the plan is the good one. Okay, so now we still have two instances of the same plan, but they're the same plan, and each one runs its own. They have the same, should be, over time, it should be the same average execution time, more or less. Okay, so that's what we got here. Now, we can actually improve it a lot better, even when we get 1.5 million rows. If we go back to the query itself, if you think about it, the best thing to do here is to add an index on creation date time, because we need to order by date time and get only the first 10 rows. So then what SQL Server can do, of course, it depends on the distribution. It can scan the index in an ordered fashion. It doesn't have to sort anything, and then filter out only the status that it needs. And after enough rows, when we have 10 rows with this status, it can stop. Okay, so this can potentially perform a lot better. And here I create this index, non-clustered index on creation date time. Let's add this index. And now, by the way, when you add an index, all the previous plans in cache that access this table now need to recompile because there is a new index. Maybe there's a better way to run this query. Now let's run it. As you can see, it runs instantly, very, very fast. Now we get an index scan of our new index. And notice that the actual number of rows is 31. Where does this number come from? So first of all, it doesn't scan the entire table. Sometimes people look at index scan and say, okay, we scanned the entire table. The table is 5 million rows. No, it doesn't scan 5 million rows. Even if you see a scan, you need to look at the actual number of rows. It only scans 31 rows and then stops. And the reason is, after each row, it goes and fetches, it does a key lookup. And in the key lookup, we compare the status ID to the parameter. So for some rows, the status ID is 2, as we wanted. For some, it's not 2. We need to throw this row away. So only after 31 rows, we get 10 rows where the status ID equals 2. And the role of this stop operator is to consume the rows. And after 10, it tells everything to stop. So the scan stops after 31 rows. And this is very, very efficient. We get only this number of logical reads compared to what I showed you earlier. Okay? So another thing you need to take from this is when you read execution plans, don't just read them from right to left and think, okay, we do a complete scan, and then we do a key lookup for each row in the table. No, you should also look at the execution flow from left to right. Okay, because the top operator starts first, it asks for rows, give me the first row, give me the next row, the next row. The nested loop says, give me the next row coming from here. Please check whether it's status ID 2. No, okay, give me the next row. Please check, yes, thank you. I will pass it to the top operator. The top operator says, yeah, I got 1 row, I need 9 more. Give me more. Okay, and so on and so on. And as soon as we get to the 31st row coming from here, and this key lookup says, okay, it's status ID 2, and the nested loop gives this row to the top operator says, okay, I got 10 rows, you can stop now. So everything stops, and we're done. Okay, so sometimes it helps to read the execution plan from left to right, not just from right to left. All right, let's move on. So I need to close some things here. You can close this. This, and let's move to this one. Cost is always estimated. Let me show you. Okay, before that, I'm using SQL Server 2019 for the sake of this demo, and everything that I showed you here is also relevant for Azure SQL Database or Azure SQL Managed Instance, in case you're using those. And there are some really cool new features in the recent versions, and specifically in SQL Server 2019. One of them is deferred compilation table variable. Okay, I will explain later, but for now I want to turn it off deliberately because I want to show you some behavior. So when turning it off, this will now behave just like, let's say, SQL Server 2017 or 16, if that is what you're using. With 2019, there is a new feature. I will talk about it later, but for now I will set it to off. And there is another stop procedure here: send fake invitations. Let me run it. Let me, of course, include the actual execution plan. And let's run this stop procedure. And while it's running, I want to show you what it's doing. Send fake invitations, this one. So this stop procedure declares a table variable called eligible members. Another one calls potential couples. This is a dating website. Okay, so what this stop procedure does, it tries to look for matches between members. Okay, so first it takes the eligible members, it takes all the members who made payments to the website, and deletes those who have a total amount of less than 6,000, so only, let's call them VIP members who made lots of payments to the website. And then into the potential couples, we take 200 random members, requesting members, 200 random members who are receiving members, and then we compare them based on, they need to be from the same country, they need to, the sexual preference of one of them needs to match the other one, they need to be the same age more or less, less than 5 years difference, and of course it can be the same member. Okay, so we try to create some matches in the dating, then we delete all the members who are not eligible members based on the deposits, the payments, and eventually we insert into our invitations, we simulate fake invitations, okay, based on the couples that we created, and we insert the invitations with all the relevant information that we need. This is the store procedure, okay? The main thing to take into account here is we rely on table variables here, okay? And it's done after 41 seconds, okay? And let's look at the plan. If we look at the plan, we actually have 5 different plans because we have 5 different statements. First, we insert into the table variable, the next table variable, and so on and so on. Sorry, this is delete, this is not an insert. So we have 5 statements, 5 execution plans. I want to talk about the cost. This one, 6% here, 52% here. So we have a cost of each operator as a percentage of the entire plan. Okay, in this case, 52% is out of this entire plan. Okay, it should result in 100% if you summarize all of them. It's not always like that, by the way. And also, if we look here, we get a query cost relative to the batch. So we get 52%. This is the cost of this entire plan out of the entire batch, out of the 5 execution plans. Okay, so this is a good place to start. If we have this store procedure with lots of statements, lots of plans, where do we start? How do we know where the problem is? It takes 41 seconds. I want to improve it. Where should I focus? On the first plan, or the second plan, and so on. If we look at the cost, the first is 52%, the third is 48%, everything else is 0. It's almost nothing. 0, 0, 0. So from this, we should focus on the first one first, right? Let's focus on the first one, which is this insert. Insert into our table variable, select from billing payments, group by. So what we need to do is to look at this query, try to optimize it, and so on. But no, I say no. I want to show you. Let's add another event session. I want to take the object ID of the store procedure. Make sure it's the same one. Yes. And now I start another event session with the SP statement completed with a filter on the object ID. So this will give me an event every time a statement inside the store procedure is completed. And then we can see the actual values of the statements in this store procedure. Okay, and again, we have this query here with X query. Currently, there's nothing, of course. Now, let's simulate the store procedure again. Okay, we run it, let it run, and I will show you, I want to compare the cost and the actual values. So if we go here, we can already see that we are done with the first 3 statements out of 5. Okay, so this is done in 1 second. This is microseconds, right? So this is 1 second. The second one is like nothing. And the third one is also half a second. Okay, but it's still running. So we are waiting now for the 4th and 5th statements to complete. 29 seconds already. Okay, we're done in 29 seconds in this case. Okay, the difference, of course, depends on what's currently running on the server, what's in cache, and so on. And if we go back here, so now we have all 5 statements. As you can see here, we still get the same values, 52%, 48% here, everything else is 0. But the actual execution times, actual duration, is something else. Out of 29 seconds of the entire store procedure, the 4th statement, this one, this delete, takes 27 seconds. But this 4th statement, it's this delete. Here it says 0%. The cost is nothing compared to the entire batch. This is a completely different story. Okay? And this is a problem you should be aware of. You should be careful relying on the cost because, as it says here, the cost is always estimated. When SQL Server produces the plan, it actually evaluates lots of options for the execution plan. It calculates a cost for each plan, and then it chooses the plan with the lowest cost, okay, the cheapest one. But this cost is estimated. It it is calculated and computed during compile time. It is only based on the estimated values. Okay, so if we look here, for example, we have estimated number of rows. Okay, it's not a good example. Let's go to our problem, our delete statement, the fourth one. Okay, if we go here, we can see that the estimated number of rows is 1. The actual number of rows is this. Okay, the cost is based on this. It's always based on the estimated values. It's based on 1. And because SQL Server thought, okay, this will have, sorry, it's here. This will have only 1 row, then I do here a nested loops. I'm going to scan this table only once. And again, in this table, SQL Server also thinks it has 1 row. Well, in fact, it needs to read this number of rows. Look at this. This is how much? 82 million rows. What a difference. But the cost is based on 1 row here, and then 1 row here. So of course, this is 0%. This is nothing. Okay, we read one row here. We do a delete. That's it. We're done. Okay. In fact, SQL Server actual needs to read 82 million rows and then perform a delete. And in reality, this takes 27 seconds. Okay. So you need to be careful because the cost is based on estimated values. And if there is a big gap between the estimated number of rows and the actual number of rows, like in our case, then the cost is actually lying to you. You can't rely on these numbers. Now, it's ironic in a way because from my experience, at least, in most cases, when you have performance issues, you try to troubleshoot performance for queries. The problem is because the optimizer was wrong in the estimation. What you actually need to do, you need to find those operators when you see a big difference in percent between the estimated number of rows and the actual number of rows. By the way, this is why Microsoft added, in one of the recent versions of SSMS, they added here in the graphical representation the actual number of rows versus the estimated number of rows. You can see those numbers here. You don't have to go into the tooltip or the properties. You can see it already in front of your eyes, and also the percentage. Okay, so this is the percentage of the actual number of rows compared to the estimated number of rows. So you can quickly scan the operators and look for an operator with a high percent or a very low percent, below 1%, of the actual number of rows compared to estimate number of rows, okay, and not at the cost, which is also a percentage. This can be confusing, okay. And again, we can see here this is a high percentage, and look at this number here. This is crazy, okay. So this is out of range. This becomes a negative number. So this is a real problem. You can see 82 million compared to 1, and this should tell you, okay, we have a problem here, actually. Not because we have 0%, this is not related. We have a problem because we have different values. Now we need to understand why. So remember that. And of course, the problem in this case is that we use table variables, okay? And I have a complete session about the comparison between table variables and temporary table. The big problem with table variables is that they don't have statistics, while temporary tables do have statistics. Since we don't have statistics, SQL Server has no way to estimate how many rows are in the table variable during compile time and also during runtime. It just doesn't know. Okay, so it needs to guess something, and there is a very simple rule. It always guesses 1 row. It doesn't matter what you have in there. Even if you have 1 million rows in the table variable, SQL Server estimates 1 row, and this is what we saw in the plan. And because of that, this can lead to really poor performance in some cases, like in our case. It takes 30 seconds or 41 seconds to run. So that's the problem. What I'm going to do, I'm going to alter the store procedure, and I'm going to simply replace every occurrence of declare table with create table, with temporary table, and change the names. Instead of the @ sign, use the hash sign everywhere, okay, like here, for example. And this is the only thing I'm going to do. Other than that, just like find and replace, okay? I don't need to change anything else in the code. Just replace a table variable. In this case, we have 2 table variables with temporary tables. Now we execute the same store procedure, and it runs for 2 seconds. Only 2 seconds. Let's look at the plan. So now we get slightly different cost estimations, but now we don't have this problem. As you can see here, we get very, very accurate estimations. The estimate number of rows and the actual number of rows is now the same. And because SQL Server now knows the actual number of rows, because it's a temporary table, we have statistics, Now it doesn't use nested loops, it uses a hash match, and the performance is a lot better, and we finish only in 2 seconds. And if we go here, so this is the first execution. This is the to create table. It's also a statement. And this is the second execution. So now, as you can see, we have kind of an even distribution of the execution times between the statements, but they are much more reliable. The cost reflects now the actual execution times in a much more reliable way. And we solved the problem. Okay. So what I want you to take out of this is, first, don't rely on the cost too much, okay? If you know that the estimations are correct, then yes, you can rely on the cost. But the first thing you need to check is not what is the operator or what is the plan with the highest cost, because this can be misleading. You need to check what is the operator with the highest gap between, highest difference between the estimate number of rows and the actual number of rows. Then you need to understand why it happened and solve the problem. In this case, it happened because we used the table variable. And this is the second takeaway from this example. Avoid using table variables as much as you can. Sometimes, yes, there are use cases for that, but in 99% of the cases, you should prefer to use temporary tables. They will perform a lot better. Okay. Now let's go back to the new feature in SQL Server 2019. This is the default. Okay. So the default is on. You don't need to change anything, and it's called the deferred compilation table variable. What this does, let me go back to the table variable version of the store procedure like before. What it does, it behaves like temporary table. It doesn't have statistics yet. It still doesn't have statistics, but at least what it does deferred compilation, just like temporary tables. So in the first execution of the store procedure, this is what I'm going to do now. It doesn't compile the complete plan during the compile time. It deferred compilation for the table variables with this new feature. Only during runtime and only during the first execution, when it gets to a statement that needs to access the table variable, it will then compile, but at this point, it knows the cardinality, the number of rows in the table variable, okay, only for the first execution. So as you will see, now it also takes 3 seconds, okay? It's not as good as with temporary tables because we don't have statistics yet, but at least if we go here, as you can see, we have a different plan now, okay? It's a little bit less optimal than what we had before, again, because before we had statistics. Now, SQL Server still knows how many rows are in here exactly, okay? But because we don't have statistics, it still comes out with a little bit less optimal plan, but it still finishes in 3 seconds compared to 30 or 40 seconds, okay? So it's a lot better. But now, anyway, we have these estimations, the number of rows. We are now going to use the same estimation each and every execution because it happens only once. Whereas when you use temporary table, if the number of rows changes dramatically between executions, you will also get recompiles to get better plans for each occurrence using temporary tables. Okay, so still temporary tables will behave better in most cases, but at least if you have an application using lots of table variables everywhere, okay, you don't want to change all of your code. By just upgrading to SQL Server 2019 or migrating to Azure SQL Database, you get this new feature out of the box. At least for all of your store procedure, you get an estimation based on the first execution and not just one. Okay, so in most cases, it will perform better. All right, let's close some stuff here and move to the third item. Yes, and yes, and yes. Let's talk about scalar function. This is another common problem with SQL Server. Again, include actual plan. Okay, so I have here a scalar function. It's called invitation rank. It accepts 3 parameters: status ID, creation date time of the invitation, and response date time. It returns a rank. Okay, so we want to rank each invitation. It's a string and varchar 10, and it has a series of if statements. So if the status is 1 and the time between the creation date time and now is more than 30 days without response time, then the rank is very poor. If the time is between 10 days and 30 days, it's poor. And if it's less than 10 days, it's maybe. If status is 2, accepted, and it's more than 30 days, it's nice, and so on and so on and so on. Okay, so we have a series of branches, and we get a different rank for each one. Very simple scalar function. We don't access any table, anything. It's just a series of if statements with some expression comparisons. And we want this logic in the function to be reused in multiple places. So it makes sense to create a function once and then reuse the function in multiple queries. Okay, it makes perfect sense. And here is an example for a query where I want to select from the invitations table, and I want to get only the excellent invitations. So I have a work clause where invitation rank with the parameters coming from each row, from each invitation. I want to rank it and see if it's excellent. And I want only the excellent invitations. So I run this. I started to get results. It takes some time. And I want to show the plan. And of course, the problem is, there are several problems with scalar functions. The biggest problem with scalar functions is that the scalar function is a batch. It's a complete batch. And what SQL Server now has to do, for each row coming from the invitations table, it has to call the function to bring it to memory, to the stack, pass the parameters from this specific row, run the batch inside the function, get the results back, move to the next row, and so on and so on and so on. So the execution of this query becomes like a cursor. It's like an iterative operation, row by row, and it performs really poor, as you can see, already 41 seconds, still running, as opposed to a set-based operation where we perform everything on the entire table as one operation. So it took 50 seconds, okay? It returned 135,000 rows. Let's look at the plan. So what we do here, first, let me show you. We do a join between invitations and invitation statuses. This is a very small dictionary lookup table with only 3 rows. Okay, so what SQL Server does, it first scans the small table with the 3 rows. It does a hash match join. And here we scan the entire invitations table, 5 million rows. And then for each row, we run this filter. If we look at the filter predicate, then we call the function invitation rank with all the parameters equals excellent. So this is exactly what we have in the where clause here. This is the filter. Now the problem, there are several problems. First, like I told you, it's row by row, so it takes a lot of time. Okay, this is not something that you can see, understand from the plan, other than looking at the text and see, oh, it's running a scalar function. I understand it's row by row. Okay, this is one thing. The second thing, the cost here, again, we talk about the cost, is unreliable. In this case, not because we have a wrong estimation. Okay, SQL Server knows we scan 5 million rows from a table. The estimated number of rows here is 5 million. It's correct. Okay, but SQL Server doesn't know the actual cost. It doesn't take into account the real cost of the function. The function is like a black box. SQL Server doesn't take into account what is happening inside the function. So I don't know exactly how it comes with a 14%, but it's not the actual cost. If you have some complicated select statements in the function itself and it has to run every time, this might still show you 14%, while in reality, most of the time, all of the time spent in this query is actually running the internals of this function. So this is unreliable. It's lying to you. It's not 76% here. Actually, the actual percentage here should be much, much higher. Okay, so that's another problem. You don't really know where the cost is, where is the problem in this query. The third problem, as you can see here, this plan is serial. It uses a single thread. Even though we scan a table with 5 million rows, if we have a very strong production server with 32 or 64 cores, we could really leverage this parallelism. We could really improve performance by running this scanning parallel, but it happens in the serial thread. This is another reason why it takes a lot of time, and this is because we use a scalar function. As long as you use a scalar function anywhere in the query, the entire plan has to be serial. SQL Server can't parallel those plans. Okay, so that's another problem, another big problem in some cases. And also, if we look at the output of this filter, so the estimated number of rows in this case is 500,000. This is the actual number of rows. This is a big gap. Sometimes it will be a huge gap. Okay, and again, because this is a black box, SQL Server can't really estimate correctly how many invitations are excellent. Again, I don't know how it comes with this estimation of 500,000 rows, okay? But usually it will be far from the actual value. And this is another problem, okay? So going forward in the plan, to the left of the filter operator, this might affect decisions of which join algorithm to use, which indexes to use, and so on, because we have wrong estimations. It can also affect memory grants. SQL Server needs to allocate memory for this hash match operator, for example, based on the input, based on 500,000 rows, while in fact it's using less memory. If we look at the property of the select operators, memory grant info. So we can see that SQL Server in this case, and it's a very simple example. Sometimes you'll have a lot worse examples. In this case, SQL Server asked for this amount of memory in kilobytes. So it's around 1.5 megabyte of memory, but it only used 352 kilobytes. Okay, this is a huge difference, okay, in percentage. So we don't really need this memory. This is a waste of memory. So lots of problems only because we used a scalar function. Now, if we take the logic from the function and we put it in the query itself like this, okay, if we want excellent, then we can look at the function and see what leads to excellent. Okay, so we need status 2, and we need the date diff to be less than 10. So instead of running the scalar function, I can simply say, write this query this way. Okay, so this is the same as getting all the excellent invitation. It returns the same number of rows, okay, but it runs only in 2 seconds. Okay, and now it's a lot better because now we don't have all those problems. As you can see, we get this scan of 5 million in parallel now, and we get a lot better plan altogether. We don't have to do it row by row, so only 2 seconds. But of course, this means we can't reuse the business logic inside the plan. This is not good because now I have to write lots of different queries with different predicates, and maybe I need this logic in different queries around the application, so this is a problem. What we can do, we can create an inline function which simulates the scalar function. It's a little bit weird, maybe. It returns a table, but this table has a single column and a single row, in this case, sorry, a case expression that simulates the previous if statements. So it does the same thing with the same logic, but it returns the results not as a scalar value, but as a table. The advantage of using an inline function is that it's a single select statement. It's not a batch. So SQL Server can optimize it within the external query, and it's not a black box. Okay. So when we run the select, the problem is we also need to rewrite our queries. It needs to use now cross apply to call the inline function and get the result as a column, invitation rank, and then we can use this where clause. So we need to rewrite the query as well. But now it's the same query with the same functionality, the same logic. It returns the same results. It runs for 3 seconds, and it looks more or less the same as the previous one. Okay, so SQL Server extracts from this query, from this function, it extracts the logic from here, and it makes it similar to this. Okay, it still has the entire case expression, so it takes a little bit more time to run, but it's a lot better than the scalar function, of course. So in many cases, you can try to rewrite your scalar functions as inline functions. But yes, this means you also need to rewrite your queries, but it will perform a lot better and you can still reuse your business logic. Now, there is another new feature, exciting new feature in SQL Server 2019, which calls T-SQL Scalar Functions Inlining. And you can check for each function whether it's inlineable or no. What this means, SQL Server can actually do this for you. You don't have to do anything. Transparently, SQL Server will take a scalar function, it will convert it into an inline function, just like I just did. So, if we look at our function, you see it's not inlineable. There are all kinds of limitations. You can check the documentation. One of the limitations is you can't use non-deterministic functions like this one, like sysDateTime or getDate. As soon as you use them in the function, it's not inlineable. And this is why we get poor performance in this case, because I'm running SQL Server 2019. So let's write something else. Let's create another function, invitation rank 2, which doesn't have sysDateTime anywhere. Okay, it's similar to the previous one. And now let's look at the 2 function. This is the first one. This is number 2. And as you can see, number 2 now is inlineable. Okay, so SQL Server can do this magic for us. So let's run the previous query with the scalar function, but this is scalar function number 2, which is inlineable, and see what happens. Okay, so we wait. It still takes a lot of time, and we need to understand why. Okay, and in this case, I want to let it complete and show you. SQL Server inlines the function, but the problem is that in some cases, inlining the function will not do any good. Maybe it will improve a little bit. Maybe it will make things even worse. In this case, it takes 27 seconds. And as you can see, it's a completely different plan. Okay, so what SQL Server did, it converted all the if statements to constant scan and lots of nested loops operators. So it's not a very nice sight. It's still okay compared to the scalar function performance. Okay, it's more or less the same, but it's not what we hoped to get. Okay, so it really depends on the code. Sometimes SQL Server can do magic and it really runs really fast, sometimes not. Let me show you some other. Let's create function number 3, which is a lot simpler. Okay, a simple case statement only for the excellent option. And we have many, I'm sure you have many use cases like that, simple scalar functions. Let me just show you that the third function is also inlineable. But now, since it's more simple, SQL Server can make it a lot more efficient. Okay, so now it takes 3 seconds, okay, with a very simple query plan as before. Whereas if I would run the same query without this feature, or I can also add this option, disable T-SQL Scalar UDF inlining for this specific statement. So using still function 3, instead of just 3 seconds, now it will take a lot of time because it's row by row, because it's a serial plan, and so on, just like before. Okay, so it will take a little time, but we need to summarize. So let me go back to the presentation. All right, so let's summarize quickly what we learned today. First of all, make sure that you compare session settings. Every session with different set options will get a different plan. And sometimes the different plan will actually be different. Okay, and when you troubleshoot something from another studio, you need to make sure that you use the same set options. Otherwise, you're troubleshooting something else, not what the application is doing. And this can really waste a lot of time and frustration. Okay, specifically arith abort, remember that it's false by default in the .NET application. It's true by default in Visual Studio. So make sure you take care of that. Remember that the cost is always estimated. The cost is calculated during compilation time. It has nothing to do with the actual number of rows. It's only based on estimated number of rows. And if you have a performance problem, and it's because you have a difference between the estimated number of rows and the actual number of rows, that the cost is actually lying to you. It's not reliable. Don't trust the cost. You should look for the gaps. You should look where you have an operator with a real difference between the estimated number of rows and the actual number of rows. Remember to do this. Okay, so focus first on this comparison and not on the cost. And avoid using table variables as much as you can, unless you really know what you're doing. There are some use cases for that. There are some rare cases where table variables will perform better than temporary table, but they are really, really edge cases. In almost all cases, you should prefer temporary table that will perform a lot better because they have statistics, and SQL Server can generate good plans for them. When you read execution plans, don't just read them from right to left. Remember to also read them from left to right. Sometimes it can really help you understand the execution flow and what's going on. When you see a scan operator, it doesn't necessarily mean that you scan the entire table. Okay, you should look at the actual number of rows read and the actual number of rows output from this operator. And also, when you look at the seek operator, it doesn't necessarily mean that you seek for only a single row. You might perform a seek operation in the index, but then you do a range scan, a partial scan, sometimes almost the entire table. So it's actually more like a scan. So this can be misleading. You need to check how many rows are affected in each operator. And the last thing, avoid using scalar functions. Now, of course, we want to write functions. They are modular. They are reusable. This is a great programming practice, but they are really horrible for performance in SQL Server when you use them in queries. So either rewrite them as inline functions or upgrade to SQL Server 2019 or migrate to Azure SQL Database, and then you can leverage the the new feature, or try to do something else. Or maybe in some cases, performance is good enough. That's okay. Just know what you're doing. Okay. Be aware of that. The scalar functions have lots of limitations. They can really affect performance. That's what I have to say. I want to thank you for the organizer of this event. Thank you to Microsoft for supporting this event. Thank you for attending. You have several ways to win prizes. Remember, you can post a selfie. You can give session. It's really important for me as a speaker and for the event organizers to get your feedback. So please provide us feedback and visit our sponsors and exhibitors. Without them, this wouldn't be possible. Thank you very much for attending. You can stay for some Q&A. I'm here for any questions. So thank you very much.